So now we'll talk a little bit more about resonance. So we mentioned it already. We said when there's more than one way to arrange the electrons, following one of those three patterns, where electrons can move from a double bond to become a lone pair, or from a lone pair to become a double bond, or the other example we said was from one double bond to another double bond. So here's an example of that. This one is C6H6. So I make a six-membered ring. I've got a hydrogen on each carbon. And when I put my valence electrons in, I find if I calculate all the valence electrons for C6H6, I've got 6 more electrons to put in. So I could think about putting them in as lone pairs. But then I would realize only the carbons that have the lone pairs have a noble gas configuration. Plus, they're not going to have a balanced formal charge. So that leads me to recognize that I need to share those as double bonds. Then I see the possibility of resonance because of this pattern where if I have a double bond between two atoms, it can shift into a position where it becomes a double bond between the two neighboring atoms. Well, then that would create 5 bonds for this carbon. So this would have to shift, and this would have to shift at the same time. So if all 3 double bonds shifted at the same time, I would get a different molecule with. So I'm not going to draw the hydrogens because they're not involved in the resonance. But now the double bonds are in different positions. That's also resonance. Right? So there's really 3 patterns that you want to be aware of and able to recognize. So back to the ozone. When I look at where the formal charges are, we calculated those before. We see that resonance allows us to draw 2 different ways that the electrons could be distributed. And this type of arrow specifically is different from one you may have seen in a different class that looks like this. It's like 2 arrows going in opposite directions, or one that looks like this. These 2 mean equilibrium. They're not the same as resonance. This arrow here is specific to resonance. It means not that those 2 structures can interconvert back and forth. It doesn't mean that. It means that neither of those 2 structures exist. What exists is the resonance hybrid, or the average of those 2 structures. And so we drew that before. So resonance is kind of like a human invention, or in other words, it's a way of us to try to visually draw structures that we can then think about in our minds. If we were to average those structures together, what does the real structure look like? Right, so in that regard, this structure is not a real thing. This is not how the electrons exist. This is not how the electrons exist. But upon drawing them, that prompts us to recognize how the electrons really exist, which is in an orbital. Since they can move over all 3 atoms, they're in an orbital that extends over all 3 atoms, and they spread out over all 3 atoms at the same time. So let's look at this example. So here we have SO3. The SO3 structure creates some formal charge. We can put that in once we calculate it. So here I've got a neutral SO3. No charge shown on the molecule, so I know the sum of the formal charges has to balance out to 0, which it does. But I can also recognize there's resonance. So you probably would have recognized that resonance as you were drawing the Lewis structure. So once you get to the point where you have all of the electrons put in on the outside on the more electronegative atom, and you've used up all your electrons, and you realize the central atom doesn't have enough, then you say, okay, I recognize the resonance because I can move any one of these 3 pairs in, and that will create 3 different structures that are only different in the location of the electrons based on these patterns for how electrons can move in resonance. So that means I've got 3 resonance contributors. So I've got the one that's shown. I've got this one here. And I've got the other possibility, which would be to make the double bond over here on the right-hand side. At this point, don't worry about the angles. Okay, don't worry. We'll talk about that next time. Don't worry for now that this is a 90-degree angle and this is more like 120 degrees. Don't worry about that for now. We'll talk about that. For now, we're just looking at the stability based on the formal charge and recognizing the fact that these three, really, none of them exist. What exists is the average. So if you wanted to look at what the average would look like, you could draw the molecule. First, you would want to draw all the electrons that are not moving. Each oxygen has at least 2 lone pairs on every structure. So there are 2 lone pairs on each oxygen that are not moving. Right? The third lone pair is the one that is either on the oxygen or sometimes it moves in. Which is really not the best way to say it, because it's not sometimes moving in. It's always moving in through resonance in an orbital that extends over all the atoms. So how do I represent that orbital? I represent those electrons moving in with the dotted line. So I have a dotted line in each one of the SO areas, of the SO bonds, because there's an orbital that extends over all those atoms that all those electrons are moving around in. In each one of my individual contributors, the sulfur has a 2+, so that has an overall 2+. That makes it a little bit unstable and reactive. That's why if I react it with water, it produces sulfuric acid, because it's not a stable structure when it has so much formal charge. How much actual formal charge does each oxygen carry? Formal charge, so, well, if we look at one oxygen at a time, this oxygen has a -1 in that structure, a -1 in this structure, and no formal charge in that structure. So 2 out of 3 of the structures have a negative. 2 out of 3. So that's a -2/3 of a charge. It's the average. What's the average of 2 out of 3? 2/3. Another way to say it is, I've got 2 total negatives, right? But they're spread out evenly over all 3 oxygens. So if I've got 2 negatives divided evenly into 3 oxygens, each one carries a -2/3. Because the -2/3 times 3 gives you that overall -2 charge. So I would have a -2/3 on each oxygen.